Um, I'm Xiaoxuan. So, hello everyone, I'm Xiaoxuan. I'm a software engineer from Meta. Today I'll talk about the Velox memory management. Here's what we covered in this talk. And first, I will talk about the high-level design goal of Velox memory system and what function it provides for query execution. Then we will go over the overall structure of the Velox memory system and its major components. And then we deep dive into each of the major memory components. And after that, we put everything together by working through an end-to-end memory allocation path in Velox. And at last, we will talk about the list of projects we plan for the next step. The Velox memory system is designed for safely running highly variable query workloads with the fixed memory resource. And we first provide memory allocation for all the queries, for query executions. And internally, we optimize large physical memory allocations by allocating memory from operating system directly. And then we optimize query memory allocation patterns by using memory arena techniques to convert a large number of small memory allocation into a small number of large allocations. And based on the automatic query memory allocation go to Velox memory system, we can actually track each query's memory usage. And based on that, we can apply the query level capacity enforcement and dynamic memory sharing between queries. When a query the memory usage go beyond the user specific capacity, we will reclaim the used memory from the query. And if the Velox memory system has no memories, then we will, based on tracked memory usage, to reclaim the used memory from the queries which use more memory for fair memory sharing. And reclaim the used memory from a running query is achieved through the disk splitting techniques which we have been built into Velox. And the Velox memory system also ensures the physical memory usage is within the total memory capacity limit. And that capacity limit is the query system that allow Velox runtime to use. And in Velox, Velox memory system provide the memory allocations from query memory and also the file cache. And file cache contains the buffer for the hot data for table scan to reuse, and also provide the buffer for the table scan to prefetch data. And in Velox, we don't require user to specify the size of a file cache, and we automatically adjust the file cache size based on the query memory usage change. When query use more memory, we'll automatically shrink the cache size. If query use less memory, we will increase we will accumulate more buffer in the file cache. The next I talk about the overall structure of Velox memory system. And when Velox runtime starts, it creates a memory manager, and the memory manager is responsible to initialize the entire Velox memory system. It creates the memory arbitrator and the memory allocator. The memory arbitrator is responsible for managing allocating the query pool memory capacity, and the memory allocator is provide a physical memory allocation for the query execution. And when the query starts running in the Velox runtime, it allocates a root memory pool from the memory manager, and then create a bunch of child memory pool based on query execution plan, which we will discuss more in detail when we talk about memory pool later. And during the query execution, the query allocates memory from the memory pool, and internally the memory pool will track the memory usage and interact with the memory arbitrator to adjust memory pool capacity based on the query's memory needs. And the memory pool allocated memory from the memory allocator. From the graph, we can see that there's two types of memory in the system. One is query memory usage, and the other is cache memory usage. As we described that in Velox, we don't need the user to configure the cache memory usage. But in practice, we need to reserve a certain percentage of Velox memory for the cache memory usage, just in case that when we shrink the cache, we have enough unpin the cache memory to free. Otherwise, there is some small amount of the cache memory pinned by the query access. On the top right, on the bottom right corner, there is a memory pushback component. That is a component we built on top of Velox runtime system, and it helps the query system like a persistent to prevent the server running out of memory. And the memory pushback component is a background daemon. It's pre-allocated to check the server memory usage. If the server memory usage above a certain threshold, then the memory pushback component will interact with, it triggers the Velox memory system to free both used and unused memory. it triggers the file cache to shrink the cache to free the unused memory. It can also trigger the memory arbitrator to free the used memory by through the disk splitting or kill the query that uses most memory to free the memory back to operating system to help the server get out of memory condition, help the server to get out of the low memory conditions. And to summarize, there's 4 major components in the Velox memory system. The memory manager, which is manages the entire memory system and provide memory pool management. And the memory pool is providing the core memory allocations and the memory usage tracking. The memory arbitrator is arbitrate the core memory capacity for the fair memory sharing. And the memory allocator is allocate the physical memory and the total memory capacity enforcement. The next step is talk about the memory pool. When the query start running, that it allocate the root memory pool from memory manager, and as we can see the graphs, that the memory pool hierarchy actually mapped to the query's execution plan. So the query context in Velox hold the root memory pool, which allocated from memory manager, and within the query, it creates one task pool for each query task. And within a query task, it creates one child memory pool for each plan node. And within each plan node, the node memory pool, it creates one child operator pool for each operator instance created from the plan node. And the reasons we create a memory hierarchy, we map the memory pool hierarchy based on the query execution plan is for the fine-grained memory usage tracking, so that we can see different type of operator, how much memory you use, and it also to ease the memory arbitration processing. And given the memory pool hierarchy and the function of the memory pool provided, we divide memory. There are 3 types of the memory pool. The first is the root memory pool, and root memory pool is responsible for the memory usage from all the child pools, and also apply the capacity enforcement and interact with the arbitrator for the memory capacity adjustment. And then the next one is aggregation pool. Aggregation pool is only responsible for memory usage aggregation from the child pool, but doesn't provide the capacity enforcement. And the task pool and the node pool is kind of the aggregation pool, and the query pool is the root pool. And the leaf pool is responsible for it actually interfaces directly with the query execution and provides memory allocations and the usage tracking. So in Velox, we provide the query level memory capacity enforcement. So the memory pool allocation has 2 steps. The first step is to update the memory usage of the new allocation and all the way to the root memory pool for capacity check. And after the capacity check passes in the root memory pool, then the memory pool can allocate memory from the allocator. So the first step, we call it memory reservations. So the simple way to implement memory reservation is for every single allocation, we report the memory usage all the way up to the root memory pool. But these will cause some problem because Velox query is multi-threaded executed, and multiple operators can run in parallel, and they allocate the memory pool in parallel, and they update the memory usage to root memory pool also in parallel. So the concurrent update to the root memory pool can causing the high log contention and associated cache coherence overhead. So we provide the quantized memory reservation. The idea is that when we allocate this, we not reserve memory for every single memory allocation. Suppose operators allocate 100 bytes. We actually reserve 1 megabyte of memory from the root memory pool. Then for the next up to 1 megabyte allocations, we don't have to reserve memory from the root pool. And these will significantly reduce the log contention overhead at the root memory pool. We have mentioned about the memory pool capacity. So actual implementation, we have 2 capacity in memory pool. One is the max capacity, which is capacity that user specified. And the other one is the current capacity, that is actually the capacity the memory pool the memory pool can use. And when we create a memory pool from the memory manager actually doesn't only allocate a portion of the capacity to the query pool. And the reason is that in the Velox, we do allow query system to over-provision the memory, so we cannot allocate all the max capacity to the queries. But during the query runnings, the memory arbitrator will guarantee the allocated query capacity is within the total query capacity limit. From this graph, we can see the space between the current capacity and max capacity is actually the capacity a query can go up to. And the space between the user reservation and current capacity is actually the available capacity to use in the query. And then the rest of the space, the blue space, is actually the actual used capacity. The last functional memory pool is memory reclaim. That is to help the memory arbitrator to reclaim the used memory from the query. And each memory pool has associated memory reclaimer. That memory reclaimer helps to reclaim helps to connect the memory pool with the associated query object. Take the operator, for example. The operator's memory reclaimer help connects the operator pool and the operator. And whenever when the operator tries to reclaim memory from the operator reclaimer reclaim the used memory from the operator through the disk splitting. So next, let's talk about the memory arbitrator. So memory arbitrator is responsible to arbitrate memory capacity across queries to achieve fair memory sharing. So it ensures the total allocated query memory capacity is within the query memory capacity limit. When we start a query, the query will get initial capacity from the memory arbitrators. And during the query execution, a query can grow its capacity through the arbitrator. There are two kinds of memory arbitrations. So if a query has already exceeded max capacity limit, so we won't reclaim memory from the other queries, but reclaim the memory from the query itself to make sure the query can run through completion within its max capacity limit. And if the query is not hit the max capacity limit, then we will go over to see all the other queries running in the system to reclaim the memory, to reclaim the used memory from the queries with more memory for fair memory sharing. The next is the memory arbitration process within the arbitrator. It consists of following steps. The first request pool will enter into an arbitration state. If the request pool is running on a driver thread, then it will put the driver thread in suspension state. And a suspension state is not considered as a running task. It is not considered a running thread in task post operation. This is to prepare for the task memory reclaim. To reclaim memory, user memory from a running task, we first need to stop the task and then reclaim memory from the task because we don't want to concurrent update to the operators, then it will cause inconsistent state. So once the driver thread is in suspension state, then later on we reclaim the memory from these driver thread. This driver thread is not considered running, then the task post can go through. The next step, once the request pool is entered into the arbitration state, the next step is to capture the memory usage from all the candidates pool. And if the request memory pool already hits the max query capacity limit, then we'll go with the local memory arbitration, try just to reclaim the used memory from the query itself. If the query doesn't reach its max capacity limit, then we will we will try to see whether there is a free capacity in the arbitrator. If the arbitrator has free capacity, then we go to the fast path to grant to grow the request memory pool by increase its capacity. And if there is no free capacity or enough capacity in the arbitrators, then we will go with a global memory arbitration, which sort all the candidate pools based on reclaimable memory and reclaim the used memory from the candidate pool with most memory usage. And at last, if the global memory arbitration still cannot reclaim enough memory, then we will pick up one of the query which has the most memory capacity in the system to board the query to let the other query to go through. And after the memory arbitration goes success, then request pool will leave the arbitration state, which put the driver thread out of the suspension state. The next slide will talk about the memory reclaimment process within a query. And the memory arbitrator just reclaims user memory from query by traversing its memory pool hierarchy. It starts from the query root pool, and the query root pool will reclaim the memory from each child task with one at a time. And the task memory reclaimer will first, before it reclaims the memory, first pause the task execution, and then reclaim the memory from each of the child name node pool with one at a time. The node memory pool will correspondingly reclaim the memory from the child pool with one at a time. And the child operator pool will reclaim the actual use memory reclaiming, and it triggers the disk splitting in the operator. And after disk splitting finish, the operator memory reclaimer will shrink the query's pool's capacity to claim the freed capacity. And after the task memory claimer is done with the memory claim, the task memory claimer will resume the task execution. So that is the memory reclaim process running inside queries. The next slide we talk about the memory allocator. The memory allocator is allocate physical memory, and it ensures the total usage, physical memory usage is always within the total memory capacity. And inside the memory allocator, we optimize a large chunk, large memory allocations. We support two kinds of the large memory allocations. One is the large continuous allocations. For that kind of allocation, we directly allocate the memory from operating systems to the map memory. And when we free the memory, we just call nmap to free those memory. And the other large chunk, memory allocation is non-continuous buffer allocation. That is most used for the string allocator, which like convert any small memory allocation into a small large memory allocations. So in that case, we don't need a very large single piece of continuous buffer. Instead, we can return user a list of a number of the non-continuous buffers with variable size. So internally, we're using size class to handle the non-continuous memory allocations. We have 9 different size class objects with the size, fixed size range from the 4 kilobyte to 1 megabyte. So each size class object only provides fixed size memory allocations. And internally, it set up initially set up in a large memory space with a space size equivalent to the memory allocator's total memory capacity. And then you use bitmap to track off each of the fixed size buffers allocation state. So on the right graph, we can see that the fixed size buffer in the size class has 3 states. It has free state and use state and map state. Initially, all the size buffer we call it class page is in the free state. And once we do allocation, allocate the free class page to the queries, then the state will change to the use state. The actual allocations might happen when on the first time the query actually write to the memory we allocate in the size buffer in the memory space of the class page. And when the queries actually free the size page back to the memory allocators, it state will mark as a map state. The map state, the operating system might still have the backing physical page for the memory space, so it will consider as a used memory. It's not a free memory. And only after we call the advice way to tell the operating system to remove the physical page back to the map memory space, then the page can consider as free. The memory allocator, to ensure the total capacity, it will consider both the used and the mapped state in the size class page as used page, so that we can make sure the physical memory usage is within the limit. And for the small memory allocation, like smaller than the 3 kilobytes, we allocate to SCD malloc, and we only expect a very few ad hoc memory query allocation will go to this category. So we mentioned that the memory allocator provide all the memory usage in the Velox runtime system, like for both like a cache and the queries. And the allocation step also takes 2 steps. So first, when the memory allocator receive a new allocation, it will first check whether the new allocation is still within the capacity limit. If it's not, the memory allocator will shrink the cache space to free up space. Then we retry the allocations and proceed. For the non-continuous buffer allocation, if we pass the memory capacity, and we still need to check whether we need to change. We need to have too many like mapped memory mapped to the class page. If I have too many mapped to the class page, then we will trigger the free to call the STM advice way to free enough like a mapped class page to the free space to make sure both allocated and the mapped class page is within the total capacity limit. The next slide we talk about the working through the end-to-end memory allocation in Velox. In the bottom left hand corner, so the query operator initiates the allocation request and it sends the action to the operator pool, and suppose the operator pool doesn't have sufficient available memory, it will send a memory reservation request all the way to the query memory pool. And if the query memory pool doesn't have enough capacity, then query memory pool will send the memory arbitration request over memory manager to the memory arbitrator. The memory arbitrator in this case find out the query already hit the max capacity limit. It triggers local memory arbitration, and then it call into the query memory pool to reclaim the memory. And in query memory pool, there is only one task and extend the reclaim request to the task one, the only task pool. And the task pool has two node pool. So on the right side hand, the node mempool has more memory. It will reclaim memory from the right hand node mempool first, node mempool 2. And node mempool 2 will send the memory reclaim request to its operator pool, and the operator pool's memory claimer actually does the use memory claim from the operator through the disk splitting. And suppose the query operator has reclaimed enough space, then we return the reclaimed bytes all the way back to query memory pool, and the query memory pool return the reclaimed bytes back to all the way back to the memory operator. And the memory operator, during the memory reclaim process, the query pool actually got shrink. So the query pool will grow the query pool's capacity and return a success all the way back to the query pool, and the query pool accept memorization from the leaf operator pool. And then at this point, the leaf operator pool can allocate a memory from the memory allocator. And suppose in the memory allocator there is no sufficient capacity, then the memory allocator will shrink the file cache to make space for the new allocation. At this point, then the allocation actually finished. Then the memory allocators allocate the buffers and send the buffer back to the operator pool, and the query pool returns the allocated buffer to the query operator. And that's how the end-to-end memory allocation works inside the Velox memory system. Here is some of the, so currently we have finished building the memory arbitrator and disk splitting and using Meta internal shared test batch scheduling, and it's run pretty reliable. So in the next step, we will focus on the performance optimization on memory arbitration and splitting. The first, currently the memory arbitration is sequential executed. So basically run one memory arbitration at a time to make sure the memory arbitration process has consistent view of the free capacity in the system. But these can cause some like cross-query execution blocking, because in the production in the scheduling environment, we see there are almost no like global memory arbitrations, but there's many local memory arbitrations. If you like do one arbitration at a time, then when one query do local memory arbitration, it will block the other queries to memory arbitration processing, and these will causing some some small queries getting blocked by the long-running memory arbitration for too long. So I think we are planning to parallelize the local memory arbitration processing to accelerate to try to avoid the unnecessary cross-query execution blocking. The other is we will continue investing in memory efficiency. So in the memory arbitration, we not only just reclaim the use memory from through disk splitting, but we also reclaim the use memory from table writer. For table writer, it will trigger the file writer to flush the struct data into the disk to free the memory. So currently we observe that the DOF writer that we're using is actually use more memory than the .java. So we will investigate how to make it more efficient to avoid early struct flush. The other, we will investigate the memory efficiency in some non-splitter operator. We still see sometimes the table scan and the partition operators will causing the query running out of memory. We will see whether there is some memory efficiency problem in those operator implementation, or we try to adding some like flow control or mechanism, sorting mechanism to make sure to cap the memory usage for those operators execution. But this splitting is on the critical path on the memory arbitration, so it's always good to optimize performance. So next step, we plan to optimize the spill data sorting, like using aggregation spill. And sometimes we see the aggregation, the sorting actually take more time than the disk I/O. So we'll consider to leverage the prefix key sortings to convert the multi-column sort to a string comparison sort. And the other, we try to optimize disk I/O itself. Like we see the spill data processing in time is comparable to disk I/O. So on write path, we consider to using write pipelining to hide disk write I/O latency from the spill data processing. Similar on the spill read path, we try to apply the read ahead to hide the read I/O latency from the unspilled data processing. For file cache, we try to like put running both the batch query and the intra query in the same cluster. For that purpose, we need to improve our current cache replacement algorithm to prevent cache pollution from one-time data scans. So instead of to leverage some advanced algorithm like arc2q, we are considered to leverage the query hints to get cache replacement. For example, the query can tell the file cache whether data is hot or not. If data is hot, we will put the data in using the applied RRU, replacement algorithms to manage the cache data. If the data is cold, we will apply the MRU replacement algorithm so that we prevent when the batch and track run together, the batch one-time data scan don't load the interactive queries data. Yeah, that's all I have. Thank you. Yeah. Any questions?
Quick question. So you had mentioned that when the memory arbitrator is called, it might reduce the capacity for a specific task that is running, especially the ones that have the more available memory. My question is, whenever something like that happens, is the way that the task actually execute change in the sense that it knows it has less memory and therefore it processes the data differently, or is it more that you end up with the tasks that have memory reduced, are they themselves become more likely to run out of memory themselves?
Oh, sorry. So you're saying when map abstraction trigger, you're saying a task can you repeat your questions?
Sure. So the memory arbitrator, my understanding is it will free up memory, and part of it can also reduce the amount of memory available to other concurrently running tasks, correct?
I think when memory abstraction happens, it basically to claim the use memory from a query, either from query itself or from the other queries. And the reclaims means that it spill the operator state, the memory state to the disk to free up memory. So it basically creates more memory space, either for the query, class query itself or some other queries.
So you spoke about the Velox memory management overall, but I think like not everything goes through the Velox memory manager. So let's say if you talk about Prestissimo, there is like ProxyGen, for example, right? Like it's like a third-party library. I believe that Meta like introduced some like throttling on for this one, just not to basically allocate too much memory for the ProxyGen. Another path is actually Parquet is using Apache Arrow, and like I think Parquet is also doing a bunch of its own allocations. And the question is around like, what is the path forward around like worker stabilities overall, like let's say Prestissimo worker stability, so that we actually can impose the total memory allocation limits properly, and we don't go actually, let's say, over some particular limits. I would say that, say, just experimentally at Uber, we were doing the shadowing of the production traffic, and we see that, let's say, if we even like we put like system memory GB to 200 gigabytes, we enable pushback, but we actually still see the workers going over 200 gigabytes over time as they actually run.
So basically, in practice, we expect most memory is managed by Velox, but there are some non-Velox component like a Prestissimo and non-Velox component like a streaming shuffle component, and also the storage client. They might allocate memory, manage memory directly themselves, probably allocate from the heap like SD malloc. For those part memory, as in practice, we just reserve some percentage of the system memory for those operations. And the memory pool, the memory pushback mechanism built into Prestissimo is to handle the spiking memory usage in those cases to translate the spiking memory usage. But if for Parquet is a large amount of memory, non-trivial amount of memory allocating from SD malloc, so we recommend to change it to using a memory pool. So Velox memory component, so I mean for the component within the Velox, it's better to allocate the memory from the memory pool instead of to allocate memory from SD malloc. Because for Parquet reader and writers, it's probably using non-trivial amount of memory. For the operator, as we see, it uses a lot of memory. If those part of memory always directly go to the SD malloc, it then probably not works well for Velox.
Yeah, but Velox Parquet reader is inside of Velox, right?
Yeah, we probably need to fix that to allocate memory through the memory pool instead of directly allocate from STD malloc. We only expect a very small amount of memory to allocate from STD malloc, but not many. So and for the non-Velox component, query system, we just reserve some system memory for those components, and also it depends on the workloads. For the spiky workloads, we provide a mechanism called memory pushback. So whenever it happens, we try to shrink memory from the Velox to give back the memory to the operating system to let those spiky workloads to pass through.
As far as I remember, for Parquet, we use Arrow to do some of the rapid calculations, but much. But sure, I mean, Arrow itself has its Arrow where to allocate from it some kind of memory pool, because Arrow has an architecture from memory pools. Some classes of Velox memory pool. Counting. It's true that there are memory users, say file system, stuff like that, that will use malloc, and what to do with malloc we don't know, and we cannot cause them to not be able to malloc, because if they couldn't. So we've been thinking about tracking the RSS. If you see it in time, you could advise away some of the memory or help to make. These are kind of always work, but find some mitigation. This problem is solved and does not fun. So we try to incoming data traffic, Proxygen, for example, we try to account for that, but because Proxygen is the one that calls malloc, we don't have. Everybody should at least use memory pools to do whatever they do, but that cannot be done in all cases, even though it should.
Have you considered making Velox allocators extensible by using maybe something like 2PMR memory resource? So if you want to use like malloc or free elsewhere, then you can track the usage of that.
So you mean using different backends, like using different memory source?
Yep.
Yeah, we have actually currently have the two memory allocator. One is the primary using persist mode is called the mmap allocators, which we manage physical memory on our own to optimize the large memory allocation. But we also have another called malloc allocator, which directly delegate memory allocation to the SD malloc. We have the memory allocator interface. So if there's some other memory source, we can also to extend that to support that. It's extensible.
Sorry, maybe I missed it in the talk. Like, have you considered like NUMA awareness for the memory allocations?
So what
Like a NUMA awareness?
NUMA.
Yeah.
Oh, that part we haven't considered yet. So NUMA, so optimize that case, yeah. But maybe in the future we can consider that.
Okay.
I would say in other systems we have dealt with if you think of a single process running multi-threaded query processing, meaning threads NUMA domain possible, but very rough all your memory and it doesn't really have a good solution. So if you have NUMA and you care about NUMA, I would say that for each NUMA node you could just run this and you pin that process to the NUMA node and then you're good. If you try to have like one thread of one process having the same address, and you pin them to different NUMA nodes, then that's a lot of hassle, and your life is going to be better if you just